Okay, well today our goal is to continue to do our code walkthrough for the project, which was due today, but is now due tomorrow. And I think it'll only take us half the time, the class time, to finish the code walkthrough, and we'll just leave it open for questions. So I hope you've all been working on the project and you've got, oh good, good questions. Yeah, I think I appreciate all the questions that you asked during the lecture, because chances are that if you have a question, then people who are viewing this video will also have similar questions. So keep those questions coming. Okay, first let's just take a second to review what we've done so far. In figure 7.43, this is like a key figure, because what it shows is the structure of an abstract code. And in this particular toy language, an abstract code could either have a concrete code of an error or an empty instruction or a unary instruction or a one-arg instruction or a two-arg instruction. And let me say that what your code should be, so let's think about what your code should be. First of all, you should have an abstract code. You should have an error. You should have an empty instruction. And then what I recommend you have is a separate instruction for a dot end and a separate instruction for, what was the other one, dot block. So I think the dot commands they behave way differently from each other, so it's good to have a separate class, a subclass for them. And then you should have another one for a unary instruction, and then another one for non-unary instruction. So that's how I recommend you set up your abstract classes. And then the instructions that have arguments, or in your example, or in PEP9 assembly language, instead of having arguments, they are operand specifiers, right? Or you could call them arguments, but anyway. And here in figure 7.43, you see we have an ident arg and an int arg. But what are the arguments for PEP9 assembly language? Yeah, hex constant or an integer constant. Yeah, so that's what you would have there in place of those, in place of ident and int. Because, we're not doing symbols. If we did symbols, I challenged you actually to do a symbol table and have this be. And if you had symbol tables, then you'd have to have an ident arg, Anyway, so that's figure 7. Any questions about this overall then? Yeah. Yes, addressing mode only non-unary instructions have addressing modes. Yeah. But see, but in addition to the addressing mode, they would have one of those two non-unary instructions. Would either have an integer constant or a hexadecimal constant. Yeah. Okay, and then we saw also that in figure 7.44, we saw how each one of these concrete codes, for example, here, this unary instruction has, in figure 7.44, class unary instruction extends abstract code, and it has a mnemonic as an attribute. And because it's unary, then it doesn't have an argument. And then over here, this one argument instruction extends abstract code, and it has a mnemonic and an abstract argument, an arg. Okay? So, and so this is just the code representation of what we saw in the UML class diagram a minute ago. And then each one of these has a generate listing and a generate code. Now, what I would like for us to do now, then, with that little bit of review, is take a look at this figure 7.46, which is the finite state machine for the parser. And the way I want to illustrate this is to do a kind of like a partial trace. So this in figure 7.46, what we're going to do is we're going to look at the code that implements that finite state machine for the parser. And let's do this. Let's say that let's do a little partial trace. And let's say that we have, in the source code, we have like capital S, lowercase e, lowercase t, set, and then we say time 15. Okay, so this is the source code, right? And we can imagine that our tokenizer is going to go and, you know, get a token for the identifier, get a token for the paren, get a token for the time. Oh, this is comma. Get a token for the 15, get a token for this. So the tokenizer will get those, and we're going to skip a lot of steps because it would take way too long to do every single step in the trace. And we will see how we parse a single line. So this finite state machine parses a single line. So here, let's take a look. So the code for the translator is here in figure 7.47. And we see this public enum parse state. So this parse state, each one of these names in the parse state, in the public enum parse state, corresponds to one of these states in the finite state machine. So your finite state machine, you know, when you draw it and you use it, you know, each state in there is represented in the code by this enum. All right, and now here's the key class. The key class is this translator. So public class translator, and we have our in buffer, which is the buffer that we've always used, and lowercase b is the letter for the object for the in buffer, and then we have a tokenizer, and so T is our tokenizer, and we've seen how the tokenizer works. Okay, it returns tokens. And then we have also, another attribute is this A code, which is our abstract code. Now this code object is going to get created each time as we go through that finite state machine. It's going to get created. And then it will be saved in a table, in a code table. All right? And then a public translator, that is the constructor, and it does the usual thing. The attribute gets what gets passed in the parameter list, so B gets in buffer, so there's our buffer gets set up. Now let's take a look at this private Boolean parseLine. Now this private Boolean parseLine is what goes through one line of code like this and creates the code record, the code object, which is then stored in the list. So let's see how it works. So first of all, we have Boolean terminate. Okay, well, first of all, we have the A code, right? So here, let's do a little partial trace here. And so here we have A code. Right? I'm going to be kind of symbolic about this. Okay, A code. And then for the local variables for parseLine, we have terminate. And then what do we have next? Arg, local first arg. So this is going to be local first arg. All right. Now I noticed a little inconsistency here. One of these is initialized, the other one's not. That's not good. I should have been consistent and initialized them both. Okay. It's a little deficiency in my code here. You see how because the local second arg is not initialized, but don't ask me why. So we have local first arg, we have local second arg, all right, and then we also have a local mnemon. So so we have a local mnemon, and what these are going to do is these are going to collect values, and as we go through, once we get through and we have discovered a valid code record, we are going to use these values in the constructor to create the code record, to create the code object. Okay, so, and now what else do we have? A token. So here's a token. And then what else do we have? A code. So now this A code gets new what? Empty instructions. So we're just going to say, let's just say empty instruction. Well, we'll just say it symbolically like this, okay? Empty instruction. And then it says parse state. So now here's our state variable. And what does this state initialize to? All right. So here is these are all the values of all of our variables when we're starting to go through this parseLine. Now let's take a look at the next part of the slide. Do. All right. So there's this one big do. And by the way, yeah, so this one big do. And then let's go all the way down. So here do, and then we have A token gets T dot get token and switch state in case PS start. And then now here on the next part of the slide we have dot, dot, dot. So there's a lot of code that's not shown here for, we don't have space to show it all. And then this other state, we'll take a look at this, case PS comma. So there's some more code there. And then case PS non-unary 2. And then at the very end of the do, it's while what? State is not equal to what? PS finished. Okay, so as long as state is not PS finished. So we saw how, that's how you finish a line of what you're trying, a line in the language, okay? And not a code instance of error. So if it's an error, then we'll finish before we get to the end of the line. And then we return what? Terminate. So now what was terminate? It's a Boolean. And it's initialized. Yeah, let's go back, we'll go back and see how it's initialized, all right? So do you see that what this does is this is a function that returns a type Boolean, but in the process of doing type Boolean, in the process of executing, of returning type terminate, which is type Boolean, it also constructs the abstract code, okay? It constructs this. And then if it was valid, it returns true. But if it's an error, it returns false. Okay, so that's what it does. Now let's go back to the top of the code then again. And, oh, we forgot to put it down. Here in figure 7.47, private Boolean parseLine, the very first thing that it does is Boolean terminate gets what? False. We forgot to write that down. But is everybody clear on that? So that terminates the loop. That's a flag that terminates the loop. Are we good? Now let's do this. Now let's go to the do loop and see how this works. See how the logic works. A token gets what? T dot get token. What's T? What was T? Remember what T was? Yeah, T was the what? What does it say here? Private what? Tokenizer T. So T is the tokenizer. What does it return? Well, it returns a token. When you say, when you say T dot get token, it returns the next token. Now, what will the next token be here? When the lexical analyzer goes, what token will it return? It will return a what? When it sees this SET, what token will it return? It will return an identifier whose value will be capital S, lowercase et. Are you with me? Okay, so it will return that. So a token gets T dot get token. So here, where's our a token? Here it is, here. So let's just say this is going to be a t-ident identifier, and whose value is set. Attribute, quote, capital S-E-T. We're just going to write that symbolically like this. Is everybody clear on that? So it's a token with that attribute. All right. And now it says case PS start. Well, what it's PS start? Where are we? PS start. Okay. So we're switching on state, and the state is PS start. So here's case PS start. If a token instance of T identifier, is that true or false? If this a token instance of T identifier, is that true or false? That is true. So what happens is, now what happens is this. We have what? Hold it. It is true. So what happens first is T identifier. So now what do we have? We have a local T identifier gets what? Now what is that T identifier in parentheses a token? That's what? Yes. It's typecasting. Okay. So that's the way I think we've seen this before, right? So the abstract token is typecast to a specific T identifier, and the T identifier token has a and so now our local T identifier gets that. So our local identifier gets this. And now that the compiler, now that we know that this is a T identifier, temp string gets what? Local T identifier dot what? get string values. So here we have, so here's our local, so now we have another local here called temp string. So temp str, and what does this temp string get? It extracts this from here. Does everybody see what that does, how that works? Okay, because that's a getter from the tokenizer. Okay, we use the getter from the tokenizer to extract it. Remember we said they're like packages. The attributes are like wrapped up in a package, and you get them. You get them with the getters. Okay, so there's that temp string has that. All right, and now if maps.unary mnemon table contains key, and what do we have? This temp. So now, and what is this passed as an argument? Temp string dot what? To lowercase. So what this gets is what? Lowercase set. Are you with me? Now, is this in our unary mnemon table map? Yes or no? No, it's not. If you go back and look at how those maps are populated, it's not, because it's not. It has two arguments. Okay, so it's not in there. So if maps.unary contains key, no. So then else if what? Maps dot what? Non-unary mnemon table dot contains key. So does that? And what are we testing? What are we checking to see if it contains? We're taking this capital SET, converting it to lowercase set, and we're looking it up in the map, right? Now, will the non-unary mnemon table contain that? Yes or no? Yes, it will. If you go back and look at how we populated our maps, that's how we did it. So our local mnemon gets now what do we get? Our local mnemon now gets what? Maps dot what? Non-unary mnemon table dot get, and what do we pass as the key? Yeah, this temp string dot to lowercase. So we are giving it the string, and it's giving us back the what? The enumerated. Yes, the enumerated mnemonic. And so our local mnemon gets what? What would this get? Here, what was the name of this mnemonic? So here, do you see here in figure 7.38? Non-unary mnemon table dot put. So lowercase set is what we gave it. It's giving us back what? Yes, it's giving us back M set, that mnemonic. All right? Is everybody clear? It's giving us back that M set. Okay, so that's local mnemon gets maps.non-unary mnemon table.get, temp string dot to lowercase, and then it does state gets what? PS function. So now state is no longer this. So it's direct code technique, right? So we're setting the state directly in the code. And this gets PS underscore function. All right? Now, and then it goes to the end of the PS start, and it does a break, and then it goes to the end of the loop. And this end of the loop says while state is what? State is not equal to PS finish, true or false? True. A code instance of error. Or sorry, not a code instance of error. Also true, so we do the loop again. So now what's going to happen is this. Let's go back to our figure 7.46. So now you see this is taking us, we started at PS start, we did the T identifier, so now we are in PS function. Now I don't want to go through the code. It would take way too long, and the code's not on the slides. It's actually not in the book either. But if you want to take a look at the code, it's all available. The entire code is available to you on the textbook website, book site. But let's just imagine what will happen. So it will be in PS function, and then and when we're in PS function, what will the tokenizer give us for the next token? It'll give us a left paren. Then according to figure 7.46, where will we go? So this PS function will change to what? What does it say there on the figure? PS what? Open is right. You see that? And then it'll get the identifier will be what? Another identifier will be what? Time. And that will take us to where? And then it will do, it will save, it'll save this. It'll get the string and save it, okay? And then just like it saved, well, it will save that in the local first arg, you see, okay? And then what will happen? The next thing we'll get is a what? Is a comma, and that'll take us to where? Oh, sorry, and then time will take us to what? PS first operand. So then this will be PS first operand. And then the comma will take us to what? There won't be any processing there, but it will change the state to PS comma. Are you with me? And then we will be in state PS comma, and what will happen at this point when we're in state PS comma? Now that we're in PS comma, then what will we scan next? A what? A T integer. Yeah, the token will be the T integer token. All right. So here now let's go back to the do, and so here on figure 7.47 it says a token gets t.get token. So what will happen then is this will no longer be t-ident. This will be ... and this will be a t integer, right? This will be a t integer with value. Now with that, instead of having string value set, what will it have? It'll have an int. It will have an int 15. That'll be its with attribute here. T integer attribute 15. Is everybody clear on that? And then it says switch state case what? PS start, blah, blah, blah. And where will this, and now here in figure 7.14, we do have case PS comma. Now is everybody, are you with me here? Because we're in state PS comma, right? So now, if a token, so here, if a token, instance of what? T identifier. Is this an instance of T identifier? No. Else if a token instance of what? T integer. So case of T integer. So now here we have a local T integer. Local T integer. So here's local T integer gets what? Oh, here. Okay. So now here we have to do the same thing. We have to typecast, right, the a token, and get that integer token, and then local second arg gets what? Now local second arg gets what? A new int arg. So here we are in PS comma, and so now here, okay, and so now here it's else if a token instance of T integer, which it is, and then this local second arg gets new int arg. So this is the constructor for an int arg. And it uses the local T integer dot get int value, so that it gets that 15. So this local second arg is an int arg, gets initialized to an int arg. So this is an int arg with 15. And earlier in the process that we skipped, that local first arg was a what? I mean, when it scanned the time and we skipped over that, what that did is for the local first arg, what was that? That was what do they call them, ident args? Yeah, I know it was an int arg initialized to 0, but on the code that's not shown here, when we actually scanned the time, we would have created instead of creating an int arg, we would have created an ident arg. See, so this would have been an ident arg. This would have been an ident arg with quote time, and this is an int arg with 15. Okay, so we would actually, when did we, here, let's go back to our finite state machine and see when that got created. That would have been created when we were in what? PS open, Are you with me? We would be in, do you see here in figure 7.46? We'd be in PS open, and we would get this we would have gotten a T identifier for this, for the token, and then we would have created this, we would have extracted the string, and we would have created a T dot ident arg. All right? So we are creating these, as we go, okay? And now, so here it says, the code says, else if a token instance of T integer, which it is, T integer, local T integer gets, we typecast a token to a T integer type so we can extract the integer, and we create this new int arg. Now, you guys, here comes the key concept. This line right here, a code gets new what? 2arg instruction. So now what are we creating? Now instead of this being the empty, now what's it replaced by? A 2arg instruction. Now it's being replaced by a 2arg, and what is being put inside that for its attributes? What are we giving? What are we giving the constructor? We're giving it a what? The local mnemon, which is what? mset. We're giving it the what? The first arg, which is this ident arg with time. And we're giving it what? The second arg, which is this. So we are creating this code object with all the attributes that we have collected as we scan to this. We have created that, okay? And so now this is a 2arg instruction. Here, let's say, actually, let's list those. With mset and what? And ident arg with time, and a what? Int arg with what? 15. And all of that is in this, all that information now is in that object. All that information is in there. Okay? Is everybody clear? And then state gets what? So what does it get? PS underscore second operand. And why does it do that? Because if we go back to our finite state machine, you see it gets PS second operand. And then what happens, and here again we aren't showing the code for the next one, but then what's the, next time it does get token, what will it return? The what? The right paren token. And that will take us to where? PS what? Non-unary 2. So this will be, boom, PS non-unary 2. Non-unary 2. And then it will get what? Oh yeah, question?
Why does it create the
Well, okay, that's a good question. An error can occur later. No, what it does is it does it as soon as it gets the information that it needs to know, assuming that it's correct. If we find out that there's an error later, a syntax error later, this will be replaced by an error argument, by an error code. We do have here in the code, we do have PS non-unary 2. So we're in PS non-unary 2 in the code here, and it says, if a token instance of what? T-empty state gets PS finish, else what? Yeah, illegal trailing character. So, oh, then we have to have an empty token. And so if we have something after the right paren, it'll be an illegal trailing character. Okay? And then what will the state be? The state will turn into what? Yeah, PS finish. So, and then while what? State is what? Not equal to parse state.ps finish, but it is finish. So it doesn't matter what the other one is because it's and, right? So that's false, so we break out the, and now what do we return? We return terminate. So what do we return? So, oh yeah, terminate is false because this is not the end one, yeah. Right, so it'll parse the next line, yeah. It'll parse the next line, okay? But so here's what it does. It returns false for terminate, but as a side effect, it has constructed this, which is all the information that we need for a code. All right, to generate the listing and to generate the code, a line of listing and a line of code. And now you guys, in figure 7.47, this you can just copy verbatim. None of this in figure 7.47 changes. All right? Because what translate does is, in a loop, it calls this process source line, right? In a loop. And so now, how does it start? Our code table is this Java type array list, okay, of A codes, abstract codes, okay? And then num errors is initialized to 0. T gets new tokenizer, initialized with the buffer B. And we have this Boolean terminate with end, which is initialized to false. And then we do b.getLine. So all this we've done before with the tokenizer. Okay, so now we are primed to start getting tokens. And then while b.input remains and not terminate with end. And now here is where we call parseLine. So we do terminate with end gets what? parseLine. And when it does parseLine, it goes through all this. And in this case, it will return false. Right? So terminate within will be false. But in the process, what will happen? This abstract code will be generated. And then what do we have on the next line? Code table dot what? Add. So that adds this to the code table.
Okay, so we're storing it with information within an array list.
Yes. Yeah. So yeah. The output of the parser and the input to the code generator is the intermediate code. So it's a list of these. That's exactly right. We're not immediately printing it out. We are storing it all. That's a good way to put it. And then if a code instance, now we inspect this. If a code instance of error, we do num errors plus plus. Okay, so we're counting how many errors we got. And then, what's the last thing before we call the while loop again? B dot what? Get line. So now we're getting the buffer ready to input another line of our source code. Okay? And then after we go through this whole loop of all these lines, we say if not terminate within. So this is what happens if the user forgets to put the dot end, okay, in our case, or end in this case, okay. So if not terminate within, then we stick a new error. We create a new A code, which is an error saying missing end sentinel, and we add that to our table, and we increment num errors by one more. Now, what you should do for your code for this time is, you see this code where it says if num errors equals 0, 0, system.out.print object code, and then for ints, blah, blah, blah. That if statement you should comment out, or just not even have it in your code yet. Because we're not doing the code generation. Are you with me? But the rest of it can be just exactly like this. If num errors equals 1, print when error was detected, else if num errors is greater than 1. Oh, by the way, do you notice out here we had singular versus plural? Okay, you don't want to say 1 errors. And then system.out.println, the program listing, new line, and program listing, and a new line. And then for int I gets 0, I less than code table.size, I plus plus. So now that's going through the code table, and it's doing what? System.out.println, or printf what? System.out.printf. And so S is the string placeholder, and it's code table.get sub I, so that gets the ith one in the code table, and it executes what? Generate listing, which we looked at the code for generate listing. So the generate listing prints out that listing code. Yes, just like, yes, we'll be using format. What was the name of the function?
String out format, since we're returning a string.
Yes, we'll use string out format, just like we did in this previous. Okay, so did you say, are there some questions now? We still have some minutes to answer questions. Yeah, okay, let's go to figure 7.53 and see what happens is, and addressing, yes, okay, that's a good question. So let's take a look at figure 7.53. How do we get an addressing mode? We start at ls start, we get a what? Comma, that takes us to what? ls addressing 1, then we can have any number of spaces after that, and then a letter will take us to ls addressing 2, and then some letters to, and so we wind up in ls addressing 2. So you know, one of the tokens that your lexical analyzer returns is an addressing mode. Right. Now, so your question is, how does that fit? Where does that fit? Let's go back, let's go here to figure 7.43. Well, we're not going to call, in your code, you're not going to call them one argument instruction, two argument instruction. What will be, instead of being called one argument instruction and two argument instruction, what will it be? It'll be unary and non-unary. So what will a non-unary, what attributes will a non-unary? Let's be very specific, since you asked. So a non-unary instruction will have what? So what attributes, the question is, what attributes will a non-unary instruction have? What will its attributes be?
Like the operator, or the,
Yeah, the mnemonic. It will be an enumerated mnemonic. Are you with me? So it will have an enumerated mnemonic. Okay? So for example, let's do an example. Suppose we are doing load word accumulator 0x0017 comma D for direct. Okay? So it will have an enumerated mnemonic. What else will it have? Yeah, yes. It will have an abstract argument, or let's call it an abstract operand specifier, which will be either a what or a what? A hex const or a int const. Hex const or int const. Either way, you can call it what you want. Yeah, I think we've been. I think you're right. I think we've been saying decimal. Yeah. Const. Yeah. But yeah. Okay. It'll be that. And not to get to your question. And what else? An addressing mode. But now, what will its type be? No. What will its type be? What will the type of the addressing mode be? Well, it's not a mnemonic, but oh, yeah. But what will its Java type be? And I hear it. String. Yeah, string is incorrect. Don't store the addressing mode as a string, because you'll need a table to convert it to what? What'd you say? Well, it's not an instruction. I mean.
Isn't that one of the things we made?
Yeah, in maps, yeah. So what will it be? So it will be a what? A what? An enumerated addressing mode. Yes. You'll have a mnemonic for it. So this is not a class. This is not an abstract anything. It's not an abstract. We don't have an abstract addressing mode with 8 specific subclasses. It's just a single mnemonic. So an enumerated enumerated addressing mode. Yeah. So it would be like AD, maybe something like AD for addressing mode underscore immediate, or I, and then addressing mode D, addressing underscore S for stack relative, or call it stack relative, or whatever. But that should be an enumerated addressing mode. Yeah, where the addressing mode, in the branch instructions where the addressing mode is optional. It will still, the branching instructions will still have this. Well, the two possible valid addressing modes for the branching are I and immediate and indexed. So this would be either, this would be one of those two in the branching instruction.
Okay, so that's still.
No. This is not abstract. This is enumerated. This is not abstract. This is enumerated.
Well, I'm wondering, like, if there's nothing like written in the source.
Well, if there's nothing written in the source, then their code will insert the I. We'll make this underscore I.
Okay, so that's the default. Is like
The default is I.
Okay, so
Oh, yeah. So
I'm
you.
trying to do like an empty instruction.
Oh, no, 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 oh, like an empty addressing mode.
yeah.
You were trying, no, there's no empty addressing mode, no, yeah. Oh, that was a good question, yeah, I see, that was a good question, yeah. Because what you want to do is internally you want to store what it is.
Yeah, yeah.
And you can just choose to not, and you can assign it to immediate if the user didn't put it, and choose not to show it, yeah. No, do not have a separate instruction type for a branch instruction that includes the addressing mode and a separate one for one that does not include it. No, that's way not good design. Instead, you always just see if the user put it, the addressing mode, and if he didn't, make it I internally. Well, no. Oh, yeah, yes, the branch instructions are all non-unary, both unconditional and conditional.
But aren't they like their own?
And if the addressing mode is missing, but it is a branch instruction, that's still legal, and you just set the addressing mode to immediate.
So we'll have to have a check.
Yes, you'll have to do that in code, yes.
Where do you think it would be best to, would you?
Well, in your finite state machine, the thing of it is that if you're looking for an addressing mode, if it's a non-unary instruction, you're looking for an addressing mode, and you don't get one, it could still be legal. So you have to make, so you look at the mnemonic and you say, if the mnemonic is a branch instruction, oh, this is legal, and the addressing mode is I.
Okay. And that's going to be in the logic portion.
In the logic of your finite state machine for the parser. Yes, direct code technique for the parser. This is a fairly complex project. But these are really good questions. Yeah, but don't call them alligators and crocodiles. I mean, it needs to, you need to make sense. Yeah, another question? Yeah, what corresponded to end here for you will correspond to dot end. So you just handle that exactly the same way. Yeah, and then there's one more, actually there's one more thing one more piece of code that is exactly identical, and that is this action performed. This action performed is also exactly identical. All it does is it sets up the buffer, sets up the translator, and calls translate. All right, good deal. See you tomorrow.